So let us begin today's session. Good evening, everyone. We are in week 8. Um, one of the feedback that I've received recently uh, uh, was uh, was that the tutorials should focus more on the problem solving element. The tutorials were a little bit uh, uh, was stressing a little bit more on the measure theoretic side of probability. One of the feedback was to um, was to lay a little bit more stress on the problem solving element. So that's what we're going to focus on uh, for the remaining duration of the course. We are in week 8, um, and since I understand that um, uh, many of you um, want these problem solving tips to do well uh, in the final exam of the course. What I'm going to instead focus on is essentially outlining strategies uh, that you can use not only to solve the assignment problems, but to solve uh, maybe a slightly more general class of problems. So let us start with the first problem that is there today. So the first problem is we're given a joint distribution of two random variables, and we want to essentially uh, compute a certain compute the probability of a certain event. Now, the first thing is that in general, we know in probability that if you're given, we are of course here dealing with continuous random variables. So in general, so let us just write in general, um, if there's a single random variable, let's call that x. So if x is is a random variable, and we know the density function of x with a PDF of f of x, then if we are asked to compute the probability of x uh, taking values in a particular set A, where A is a subset of Rn, then of course we know that this probability is given by integral. Uh, the integral is over A, which is a subset, and of course we use the density function. Right. So this is how we generally compute the probability of x taking values in a particular set. And A, of course, is a measurable set. So A belongs to B of R over here. Now, in order to do this for the case of two random variables, or in general for a multivariate case, uh, so let us say in the uh, say x1 to xn are random variables with a joint PDF f. So f is a joint PDF. F is a function from Rn to R. So now if we take an event, so now let A as a subset of Rn, and A of course being uh, and A of course being a Borel subset of Rn. If we ask what is the probability um, of this event, that x1 to xn should belong to A, then in a similar way, this is equal to uh, the joint PDF, or let's just say, let's write it in this way. So now coming back to this problem, we are of course here, we are given two random variables x and y, and the event whose probability we want to compute is this event, which is the sum of these two random variables is greater than 3. Okay. So the first step over here is computing the joint PDF of x and y. So first, let's compute. This is step 1. Compute the joint PDF, and the joint PDF is given as the partial derivatives. So f of x comma y is equal to del square del x del y of fxy at of course x comma y. So let's do that for this function. That is equal to um, del upon del x of del f upon del y. So that is equal to del upon del x of and that is equal to um, e to the power minus x plus y. So now, of course, we now have the joint PDF f, that is. So we want to compute the probability of this event, which is x plus y being greater than 3. And as usual, we're going to use the PDF. So that is e x plus y dx dy. Now, of course, this integral exists, and so by Fubini's theorem, you can solve it in an iterated manner. So that is equal to it's of course given that x and y are positive random variables. So so you can either you can integrate uh, either you can integrate dy first, keeping x constant, or the other way around. So this is equal to integration 0 to infinity. Let's say you are uh, let's say you are integrating y by keeping x fixed. So if you keep x fixed, then y varies from y is of course greater than 3 minus x. Um, so y varies from 3 minus x to infinity. Then of course you have this density function f xy dy dx. So that would give you the probability. Okay, so this should be like a general strategy that you first compute the PDF and then you proceed with a computation. Often that computation would involve double integrals or uh, multiple integrals in general. You have to solve them iteratively, and Fubini's theorem in these cases will almost always hold. So now let's look at another problem, which involves discrete random variables. And here, of course, we are asked to compute a conditional probability mass function. So, so going by the standard definition of conditional probability, the probability of x being equal to x, given that y is equal to some constant, a, let's say, is equal to probability of x equal to x and y equal to a divided by the probability of y equal to a. Right? So the probability of y equal to a is essentially obtained by marginalizing this. Uh, let me write it down. Is the is obtained by marginalizing over x. So that is equal to in general, if you have like a discrete random variable, so that would be equal to sum over of probability of x equal to xi y equal to a where this set xi is essentially the set of uh, discrete values that the random variable x takes. So in this case, uh, this would be equal to, so the probability, let me write it down, is the probability of y being equal to 2 is essentially the sum over of probability of x be equal to I, um, and y equal to 2, where I is from 1 to 3. So of course, using uh, the joint distribution, we can compute this probability of y being equal to 2. And um, and of course, then using the definition of conditional probability, uh, we we can compute the conditional probability mass function. Okay, so let's look at the fourth problem. So here we have a joint distribution of discrete random variables, but of course x and y both take values in the set 0, 1. And we are given a bunch of data, and we have to recover the joint distribution of x, 1. So, I mean, if we're talking about it a little bit greater generality, if we so if we know the conditional probability and the marginal distribution, we can recover the joint distribution, right? In other words, if I know the probability of y be equal to y given x equals to x, and if I know the probability of x equals to x, then of course I know by the definition of conditional probability, I know that the probability of y being equal to y and x being equal to x is just given by the product of the conditional probability uh, and the marginal. So with this in mind, we have to essentially figure out the conditional probability and the marginal distribution. So it is given to us that probability that x takes value 1 with probability 0.6. Now x of course takes two values. So it has to take the value of 0 with a probability of 0.4. Right? So we have obtained the marginal distribution. Now, of course, uh, we want to get the conditionals. So, of course, the conditionals will involve the two variables, um, x and y. So this is given to us, probability of y being equal to 0 given x equals to 1. Now the conditional probability is an actual probability. So if we were to say, if we want to compute probability of y equals to 1 given x equals to 1, and the probability of y equals to 0 given x equals to 1, then that should sum up to 1 because it's a probability. And so we get the probability of y equals 1 given x equals 1 is 0.7. Similarly, we are given the probability of y equals 1 giving x equals 0. We can similarly obtain the probability of y equals 0 giving x equals 0. So once we have done that, we have obtained the conditional probability, and we have also obtained the marginal, and so that allows us to compute the joint distribution of x over y. Okay, let us say that x and y are continuous random variables, and we're given the joint density function of x and y. So fxy, the joint density function, is given to us. So now we want to compute the conditional density function. So the conditional density function p y given x comma x is defined as the joint density function, or let's use small f only. So it's defined as the joint density function fxy um, divided by um, the density of the marginal distribution of x. Okay, so this is the um, density of the marginal on x. Now, of course, the marginal on x is obtained. So if f, the capital F subscript x is the marginal, so then this marginal is essentially the probability of x being less than or equal to x. So uh, if you have the density function, then that is just given as integral over 0 to small x, and y varies freely. Sorry, integral from minus infinity to x. I'm talking about the general case, minus infinity to x, and y varies freely. So that is, of course, your so that is, of course, the marginal on x. Now the density f of x is the derivative uh, of this marginal, and so that is equal to integral minus infinity to plus infinity fxy xy dy dx. So you obtain the density of the marginal by simply integrating this density with respect to y. And uh, for this problem, this is precisely what you have to solve. So in this particular problem, what is given to us is that um, okay, so it is given to us that uh, y varies from 0 to twice x, and x, of course, lies in 0 to half. So of course, you have to keep these constraints in mind uh, when solving for uh, the PDF. So in general, the PDF over Well, I mean, the PDF is defined in this way. The PDF fxy for x greater than half, um, the PDF is just equal to 0. So you have to set the limits of this function appropriately, and that would give you uh, the the density of the margin. In other words, in this case, it's just going to be equal to for a given x, um, for a given x in 0 to half, right? Okay, so should be clear how to solve this problem. Yeah, in general, you have to recall the definition of the conditional probability density function, which is very similar to how we define a conditional probability, except in this case it is for densities. Um, and then if you integrate the joint PDF, that gives you the marginal PDFs. Okay, so here again we have a similar. Oh, sorry. Oh, yeah, yeah. Okay, again we have a problem like this. Um, um, Not concluded the answer. Can you tell me what do you mean? You can unmute yourself. So okay, so I will not I will not solve the exact assignment problem. This is an assignment problem. I'm not going to solve and give the exact answer of the assignment problem. If that is what you are referring to, uh, I won't do it because uh, my understanding is that the submission date of the assignment is after the tutorial session. So I would essentially be spilling out the solutions if I do that, uh, which of course would be in violation uh, of the rules. Um, So my purpose here is to essentially give you like strategies, discuss strategies to solve this. And then I'm also not going to talk about all the assignment problems. I'm going to talk about a subset. Uh, and then more or less you have to use the ideas and strategies that I discuss in the session uh, to to use to the complete set of problems. Okay, so let's look at this problem. It is again of a similar kind, um, except that uh, except that the subset that you're dealing with. So if you're talking about this particular subset, so here of course we have y that takes values from 0 to 2x. So if you can draw a picture over in this particular problem, you can draw a picture where x, this is sort of the xy plane, x is from 0 to half, and then uh, y takes values from 0 to 2x. So uh, you have this range within which this PDF is defined, which is this fxy. And outside the PDF is just equal to 0. Over here, the PDF is defined in this way. You have x from 0 to 1 and y from 0 to 1. So you have this square region. So this is where the PDF is defined, and the PDF is equal to twice x. Uh, of course, you can check that this is a PDF. If you integrate it over the square, you should get exactly equal to 1. And now we again have to compute this conditional probability. So the conditional probability over here, of course, now there are two kinds of events. There's one kind of event which involves just one of the variables, and the other kind of the event involves both the variables. So let's look at the first kind of event. The first kind of let me just write. Let me let me just write. I mean, this is not like any standard notation that we get there. It's just like notation that I'm cooking up right now. So you have two kinds of events. So the first kind of event is events involving uh, the two random variables, and you have a second kind of event which is involving just one random variable. So for events involving one random variable, this is something we know, right? In particular, x, this event x less than equal to half. If we were to compute the probability of this event, then that is by definition equal to uh, the uh, the distribution function of x, which in this case can be obtained by marginalizing the joint PDF. So in other words, you obtain so in other words, f of x at half is obtained by integrating x from 0 to half, and then y, well, y, you're essentially marginalizing over y. So y can vary from 0 to 1 in this case. And then you have the function over here, twice x times dy dx. So that gives you this probability. The second kind, so this is for the second kind of event. For the first kind of event, which involves two random variables, in this case, it is the sum of the random variables being less than or equal to half, less or equal to 1. In order to uh, in order to solve these kinds of in order to compute the probability of these kinds of expressions, what you do is that let's say you fix x first. If you fix x, uh, then y varies from 0 to 1 minus x, right? um, so, I mean, if you write down this as a probability, this is equal to integral over this event, which is x plus y less than or equal to 1. This is an event. And of course, uh, you are going to use the density function, which is fxy dx or yeah, dx dy. Now, because of Fubini's theorem, what you can do is you can, of course, uh, integrate this iteratively. So this is equal to, uh, this is like an iterated integral, minus infinity to infinity, again minus infinity to infinity. But you are not integrating over the whole set. You're integrating it over just this event. Okay. So let's say you write it down in this way: 1 x plus y less than or equal to 1 dy dx. Okay. So let's say you solve the function. Okay. So this is an indicator random variable. So not a random variable. This is an indicator function, which is one only if this relation is satisfied, and is zero if this relation is not satisfied. So you can see that this is like a nice way to sort of represent this integral. Now, when you're solving for this inner integral, then x is fixed. So once you fix this x, this one, so this one x plus y less or equal to 1. So this thing is equal to 1 when y varies from 1 minus small x to 0, right? So, so you write it as um, as integral minus infinity to infinity. You let y vary from 0 to 1 minus x. Then the um, then the density function dy dx. Now, of course, this density function is 0 if x is outside if x is outside the interval 0, 1. So so this becomes integral over 0 to 1, and y varies from 0 to 1 minus x. So we have the density function given by twice x times dy times dx. And of course, that gives you the probability of this event. Now you know the probability of this event, the probability of this event. You can compute the probability of the conditioned event. So the key thing over here is this. So whenever you get expressions of this kind, you have to typically solve these double integrals or multiple integrals, and you can solve them in a staggered way. So you fix one of the variables and you solve for the other variable. So when you're solving for the other variable, the range is something you have to decide. So if you could have also done it the other way around, where you, let's say you fixed this y and you let this x vary from uh, 0 to 1 minus y. And and the manner in which you and the manner in which you carry out the integration, so whether you integrate dy first and dx later or the other way around, uh, is does not change the the result of the integral, as long as this integral exists, which is always the case because you're dealing with these problem principles. So yeah, Fubini's theorem. However you want to manipulate it, you can do it in this way. Sometimes choosing a particular order in which to do the integration can sometimes lead to uh, evaluating an easier integral over a harder integral. Okay, I hope this is clear. Then there is problem 7, which is again similar to problem 6. Now let's look at another problem. So here again, we are given a joint a, a, uh, a joint distribution with a joint PDF given to us, and we want to compute the covariance of x comma y. So recall the definition of covariance. Covariance is defined as expectation of uh, x minus the mean of x uh, times the expectation of y minus the mean of y. And that just becomes equal to the expectation of xy minus the expectation of x times the expectation of y. So if you go by the formula for expectation of x is equal to uh, integral over x, then the density function for x dx. The density function for x and y are obtained by marginalizing. So you marginalize this joint PDF uh, using what we have seen in the previous problems to obtain the the density function for just x and y. Once we obtain the density function of x and y, we know what the expectation looks like. So the term that remains to be computed is expectation of xy, and that is just equal to, it's not just expectation of xy. In general, if if we have a function of these two random variables, so if you have like h of x comma y uh, is a function of x comma y, then expectation of this this function h x comma y would just be equal to uh, integral minus infinity to infinity h of x comma y times this joint PDF. Now, of course, h x comma y in this case is just equal to the product xy. So you just have to this amounts to just uh, solving solving um, solving the integral. But of course, in this case, something I just noticed right now is that the random variables here are discrete random variables. So you just repeat this procedure for discrete random variables. There's no need here, of course, to compute PDFs because they're discrete random variables. Instead, you can just simply compute the mean as so you can just simply compute the mean expectation of x as equal to sum over of um, xi probability of x equals to xi, which in this case is just 1 and 2. And the probability of x being equal to xi is again just obtained by marginalizing the joint probability function. All this that I wrote over here applies for continuous random variables. Right. For instance, uh, this problem. For instance, this problem where now we are given uh, a joint probability density function, and you have to compute the covariance between x and y. So this is precisely when uh, this kind of analysis would be used. Let's look at this problem. X and Y be random variables with the variance of X and Y be given to us. Right. So the variance and the covariances are given to us. So we have expectation of x squared minus expectation of x whole squared, which is the variance of x equals to similarly for y, and expectation of xy minus expectation of x times expectation of y also equal to 2. Now, okay, the covariance of z comma x is equal to uh, the expectation of zx minus expectation of z times the expectation of x. Right. Now, covariance is, of course, it is a uh, it is of course a bilinear function of z and x, bilinear over real numbers. So so you might just write covariance of z comma x to be equal to covariance of x minus 2y comma x, which is equal to covariance of x comma x minus twice the covariance of y comma x. So this is given to us, and the covariance of x comma y, covariance of y. So covariance is, of course, it's a symmetric bilinear. Uh, yeah, I mean, covariance is essentially a symmetric bilinear uh, function on x and y. So that allows us to compute the final covariance. So covariance of x comma y is just the variance of x, and of course this quantity is given to us. So that brings us to the end of um, today's discussion. Not really well today, so I don't see anyone else. So I would end today's session. Thank you.